In mathematics, the Klein 4 group, often symbolized by the letter V or as K4, is the group Z2 times Z2, the direct product of two copies of the cyclic group of order 2. It was named Vierergruppe by Felix Klein in 1884. The Klein group's Cayley table is given by. The Klein 4 group is also defined by the group presentation. All non-identity elements of the Klein group have order 2. Thus any two non-identity elements can serve as generators in the above presentation. The Klein 4 group is the smallest non-cyclic group. It is however an abelian group, and isomorphic to the dihedral group of order 4. It is the only dihedral group that is abelian. The Klein 4 group is also isomorphic to the direct sum Z2, so that it can be represented as the bit vectors 00, 01, 10, 11, under bitwise XOR. Note that 00 is the group's identity element in this case. The Klein 4 group is thus an example of an elementary abelian 2 group, which is also called a Boolean group. The Klein 4 group is thus also the group generated by the symmetric difference as the binary operation on the subsets of a power set of a set with 2 elements, i.e., over a field of sets with 4 elements, e.g., the empty set is the group's identity element in this case. Another numerical construction of the Klein 4 group is the set 1, 3, 5, 7, with the operation being multiplication modulo 8. Here A is 3, B is 5, and C equals AB is 3 times 5 equals 15, 7. Geometrically, in 2D the Klein 4 group is the symmetry group of a rhombus and of a rectangle which are not squares. The 4 elements being the identity, the vertical reflection, the horizontal reflection, and a 180-degree rotation. In 3D there are 3 different symmetry groups that are algebraically the Klein 4 group 5, one with 3 perpendicular two-fold rotation axes, D2, one with a two-fold rotation axis, and a perpendicular plane of reflection, C2H equals D1D, one with a two-fold rotation axis in a plane of reflection, C2V equals D1H. The 3 elements of order 2 in the Klein 4 group are interchangeable. The automorphism group of V is the group of permutations of these 3 elements. The Klein 4 group's permutations of its own elements can be thought of abstractly as its permutation representation on 4 points. V equals, in this representation, V is a normal subgroup of the alternating group A4 on 4 letters. In fact, it is the kernel of a surjective group homomorphism from S4 to S3. According to Galois theory, the existence of the Klein 4 group explains the existence of the formula for calculating the roots of quartic equations in terms of radicals, as established by Lodovico Ferrari. The map S4-S3 corresponds to the resolvent cubic, in terms of Lagrange resolvents. The Klein 4 group as a subgroup of A4 is not the automorphism group of any simple graph. It is, however, the automorphism group of a 2-vertex graph where the vertices are connected to each other with 2 edges, making the graph non-simple. It is also the automorphism group of the following simple graph but in the permutation representation, where the points are labeled top left, top right, bottom right. In the construction of finite rings, 8 of the 11 rings with 4 elements have the Klein 4 group as their additive substructure. If R times denotes the multiplicative group of non-zero rails and R plus the multiplicative group of positive rails, R times R times is the group of units of the ring R times R, and R plus times R plus is a subgroup of R times R times. The quotient group is isomorphic to the Klein 4 group. In a similar fashion, the group of units of the split complex number ring, when divided by its identity component, also results in the Klein 4 group. In music composition, the 4 group is the basic group of permutations in the 12-tone technique.